Usually when we talk about a video game ocean, there is this underlying expectation of a kind of digital sleight of hand.
Right. Yeah, totally.
Like you look at the horizon, you see the waves rolling, and the light is glinting off the crests, and for a second your brain just accepts it. I mean, you really feel like you are looking at the sea.
Because it's designed to trick you. It's theatrical.
Exactly.
Yeah.
But underneath that immediate impression, it is a trick. Historically, it has literally always been a trick.
Oh, absolutely.
It is a flat, invisible plane with like an animated texture painted on top of it, or maybe a repeating loop of 3D geometry doing a carefully synchronized dance.
Yeah. It is a backdrop designed to look like water just for a passing glance. But if you actually interact with it, if you try to put a boat on it, it doesn't behave like water at all.
Right.
The illusion shatters the exact moment you try to apply real-world physics to it. I mean, the older techniques were entirely about painting a compelling picture of an ocean, not actually simulating the ocean itself.
And that illusion is exactly what we are shattering today.
Yes, we are.
Because when you step into the world of modern GPU-driven physical simulations, that whole theatrical backdrop just disappears. We are no longer looking at a clever animation loop.
Not at all.
We are looking at a computational landscape that is, frankly, staggeringly complex. We are moving from painting a picture to simulating the actual underlying physics of the ocean.
Mathematically.
Right, mathematically, molecule by molecule, in real time.
Which is the absolute definition of a paradigm shift in real-time rendering. I mean, the computational horsepower required to stop faking it and start actually calculating the fluid dynamics of a churning sea is immense.
That's wild.
We are talking about tracking thousands of overlapping wave frequencies, computing localized buoyancy for complex rigid bodies, and, rendering physically inaccurate light refraction, all simultaneously.
And that brings me to why we are here and who we are talking to. I want to send a massive enthusiastic welcome to a very specific group of listeners joining us for this deep dive.
Oh, yeah.
The Buoyancy Sigma Scholars of Edward Little High.
Welcome, everyone.
We know you are tuning in because you share our absolute obsession with the intersection of computer science, advanced physics, and high-level mathematics.
It's the ultimate flex, honestly.
It really is. You guys want to understand the bleeding edge of browser technology, not just on a surface level, but down to the core algorithms.
And it is a fantastic subject to tackle today, because what we are about to unpack is not something running on $1 million university supercomputer.
Right.
It's not pre-rendered over weeks in a Hollywood visual effects studio either.
No, so picture this. Just picture a visually stunning, physically accurate ocean. The water is deep, it's dark, and it's churning. A boat is dynamically bounding across the waves, crashing through the crests and rolling heavily into the troughs.
You can almost feel it.
Right. And the phone is breaking dynamically, not because an animator drew it, but based on the actual mathematical compression of the water surface.
Yeah.
Light is refracting through those waves, casting precise, shifting caustics on the seabed below. And this entire chaotic physical ecosystem is running natively in a standard web browser.
In real time.
In real time, on a standard off-the-shelf laptop.
I mean, even 5 or 6 years ago, that specific claim, doing all of this natively within the constraints of a web browser, would have been considered computational science fiction.
Oh, completely.
The browser environment was just notoriously bottlenecked, but a massive technological leap has occurred.
And our mission today is to deconstruct exactly how this leap happened. We're going to journey through the mathematical foundations of 6 degrees of freedom buoyancy modeling, and we're going to explore how the revolutionary WebGPU API is completely upending the graphics world to make these simulations a reality.
It's going to be a heavy lift, but it's fascinating.
But before we can drop a boat into a digital ocean, we have to actually build the ocean itself.
Obviously.
And if we aren't just drawing waves, where do we even begin?
Well, we begin with a pivotal shift in computer graphics history. You have to trace this back to the late 1990s and the work of a researcher named Jerry Tessendorf.
Okay, Tessendorf.
Yeah. If you have seen the 1997 movie Titanic, you have seen the genesis of Tessendorf's work.
Oh, wow.
He introduced what we call a spectral simulation approach to rendering oceans.
Wait, so before Tessendorf, if a game developer or a visual effects artist wanted to make water, what were they doing? Because I keep seeing the term Gerstner waves in all the research.
Right. So Gerstner waves or tricoidal waves were the industry standard for a very long time. And the concept is fairly straightforward, honestly.
Right.
You basically explicitly tell the computer to draw a wave. You create a mathematical function, usually just a modified sine wave, and you say, here's a wave moving north at 5 meters per second, and here is a smaller wave moving east at 2 meters per second.
Okay, that makes sense.
And then you just stack maybe 8 or 16 of these distinct waves on top of each other, and you add up their heights at any given point on your 3D mesh.
But doesn't that sound like a recipe for a very predictable ocean? Like if you are just layering a handful of explicit shapes, wouldn't the pattern just repeat endlessly?
Yeah, that is the exact problem. It completely lacks the chaotic, organic energy of a real sea.
Right.
A Gerstner wave ocean has a very distinct, repeating, almost plastic look to it. Like, you can stand on a virtual beach and watch the exact same wave formation roll in every 30 seconds.
Oh yeah, I've definitely seen that in older games.
Exactly. So Tessendorf's breakthrough was realizing that real oceans do not behave like a handful of stacked sine waves. He shifted the entire industry away from explicitly drawn procedural waves and moved toward statistically driven spectral simulations.
So instead of explicitly drawing the shape of a wave, we were doing something entirely different. We were basically writing a complex statistical recipe.
Yes. We move away from the spatial domain, which is the physical 3D space we can actually see, and we move into the frequency domain.
Frequency domain.
Right. We start using mathematical models derived from actual physical oceanographic observations. And two of the most famous are the John-Swap spectrum and the Phillips spectrum.
Okay, let's break that down for the scholars, because the idea of a spectrum can be pretty abstract.
Sure.
These models don't describe the physical shape of the water surface, right?
Yeah.
They describe the distribution of wave energy across different frequencies in different directions for a specific patch of ocean.
Think of it like a highly detailed weather report for a very specific area of the sea.
Okay.
The John-Swap spectrum takes in environmental variables and outputs a massive grid of data that essentially says, in this area, there's a massive amount of energy pushing long, slow waves toward the north and a chaotic scattering of high-frequency energy, creating small ripples in every other direction.
I was looking at the specific physical parameters these statistical models use, and it is fascinating because it is pure foundational physical science.
Yeah.
Like, we are plugging in the average wind speed in meters per second. We're plugging in the ocean depth. We factor in standard surface gravity, which is, your classic 9.81 meters per second squared.
Good old 9.81.
And we use the water density, generally around 1,000 kilograms per cubic meter.
Right.
But there's one variable that really stood out to me. Fetch.
Fetch.
What exactly is fetch in this context? Because it sounds important.
Fetch is perhaps the most crucial concept in understanding how real ocean waves actually build up over time. It basically represents the contiguous distance over which the wind has been blowing across the open water.
Without hitting anything.
Right, without hitting an obstruction, like a landmass or a huge island.
So a storm brewing in the middle of the Atlantic Ocean is going to produce wildly different waves than a heavy wind blowing across a small inland lake, even if the wind speed is completely identical.
Because of the fetch. A longer fetch allows more time and way more surface area for the kinetic energy of the wind to transfer into the water.
That makes so much sense.
Yeah, that continuous energy transfer is exactly what creates those massive, terrifying, long-period swells you see out in the deep ocean.
Right.
So by feeding the fetch, the wind speed, and gravity into our John-Swap spectrum, we generate a mathematical grid of complex numbers. And these numbers represent the amplitude and the phase of thousands of different overlapping wave frequencies.
But wait, we run into a major conceptual roadblock here, don't we?
We do.
We have this beautiful, highly accurate wave spectrum, but it is entirely in the frequency domain. Like you said, it is just a grid of energy distributions. We can't render a frequency domain on a screen.
No, you can't see energy distributions.
To actually draw the ocean, we need physical heights, we need the spatial domain. So how do we translate that energy map into physical 3D geometry?
This is where the heavy mathematical lifting comes in. We use an algorithm called the inverse fast Fourier transform, or IFFT.
I have to admit, the Fourier transform is one of those concepts that can completely melt a person's brain if you stare at the math too long.
Oh, for sure. It's intense.
How do we visualize what this is actually doing for the Sigma scholars listening?
Let's try to visualize it without writing out the raw calculus. The standard Fourier transform is just an operation that takes a complex signal and decomposes it into its constituent frequencies.
Okay.
The classic analogy is a musical chord. When you strike a chord on a piano, your ear hears one unified, complex sound.
Right.
But if you run that sound through a Fourier transform, The math pulls that complex sound apart and hands you back the individual isolated musical notes, the specific frequencies that actually make up the chord.
Okay, I follow that. That's a great analogy. So the inverse fast Fourier transform just runs that process in reverse.
Yes, exactly. We hand the algorithm the individual notes. In our case, the notes are the thousands of different wave frequencies and amplitudes generated by our John swap spectrum.
Right.
And the IFFT takes all of those separate frequencies, overlaps them, calculates exactly how they interfere with one another, and reconstructs the complex chord.
And in this context, the complex chord is the physical, rippling, chaotic 3D surface of our digital ocean.
Bingo.
The IFFT basically spits out the spatial domain data, the literal physical elevation of the water at every single point on our geometric grid.
But calculating this transformation for hundreds of thousands of grid points and doing it 60 times a second to maintain a smooth frame rate, it is an astonishing amount of computational work.
That sounds impossible.
If we just blindly fed data into the IFFT, the simulation would immediately crawl to a halt.
Which is why the researchers use a brilliant mathematical shortcut, right?
Yeah.
One that's tied to the nature of the data itself. It relies on something called the Hermitian property.
Yes. This is a beautiful piece of signal processing theory that saves us an enormous amount of processing time.
Let me see if I can explain the core concept here, and you correct me if I'm off.
Go for it.
Because our final desired output, the physical height of the water surface, is a real physical measurement. It is represented by a real number. It is not an imaginary number. And because the end result is purely real, the spectrum in the frequency domain must possess a specific symmetrical property, which mathematicians call being Hermitian.
Right. The function at a negative frequency is the exact complex conjugate of the function at the positive frequency. Basically, there is a mirrored structure built right into the data itself.
So because of that built-in symmetry, we don't actually have to calculate the inverse Fourier transform for every single value independently.
We don't.
If we have two completely separate sets of data we want to transform, say, we need to calculate the wave height, but we also want to calculate the wave slope at the exact same time, we can pack one set of data into the real part of our calculation and pack the other set into the imaginary part.
Yes.
We essentially shove two separate problems into one mathematical suitcase, run the IFFT once, and then just unpack the two separate answers on the other side.
That is perfectly explained. We calculate the inverse Fourier transform of two distinct functions at the exact same time, literally halving the computational workload.
That is incredibly elegant.
It is an incredibly elegant optimization, and frankly, we desperately need that halved workload because simulating a realistic ocean requires much more than just calculating vertical height.
Right, because if you look at actual footage of rough seas, or if you have ever bobbed in the ocean during a storm, the waves aren't just hills of water moving straight up and straight down.
Not at all. As a wave crest, the mass of water actually surges forward horizontally, and then it pulls back underneath in the troughs. It is a circular rolling motion.
Orbital motion.
Exactly.
Like if you throw a cork in the water, it traces a circle as the wave passes. It doesn't just ride an elevator straight up and down.
Right. To capture that organic behavior, we cannot just use the IFFT to calculate vertical displacement. We also have to calculate a completely separate horizontal displacement vector.
Okay.
By taking the vertices of our 3D ocean mesh and offsetting them laterally as well as vertically, the geometry of the waves physically compresses.
And that lateral compression is the secret sauce, isn't it?
It really is.
It takes a smooth rolling hill of water and just pinches it. It sharpens the wave crests, making them look peaky and threatening, while simultaneously widening out the troughs between the waves.
Yes.
It completely eradicates that perfect symmetrical sine wave look and creates the sharp, chaotic, choppy reality of the open sea.
And here's where things get really intense if we step back and look at the sheer scale of the math we are discussing right now.
Oh boy.
Generating statistical spectra from wind data, packing complex numbers to exploit Hermitian symmetry, executing multi-cascade IFFTs to get both vertical heights and horizontal displacements for hundreds of thousands of vertices.
Every single frame.
Every single frame. This workload would absolutely melt a standard computer's central processing unit.
Right, because a normal CPU is designed to handle tasks sequentially.
Yeah.
Maybe juggling a few dozen threads at a time if you have a great chip.
Exactly.
Trying to calculate this much overlapping fluid math on a CPU would turn a laptop into a space heater and give you maybe one frame of animation every 10 seconds.
Which is the fundamental reason why, to make this run natively in a browser, we need a complete architectural paradigm shift.
A completely new approach.
We simply cannot rely on the CPU for the simulation. We have to unleash the raw, parallel processing power of the graphics card. We have to move everything to the GPU.
And this brings us to Act 2, basically, a massive technological leap that is actively reshaping the internet right now.
It's revolutionary.
For any of the scholars trying to understand modern web graphics, you have to understand the transition from the old standard WebGL2 to the new powerhouse WebGPU.
The magnitude of this transition really cannot be overstated. For a very long time, WebGL2 was the absolute gold standard for rendering 3D graphics in a web browser.
Right.
But WebGL2, at its core, is an API designed specifically for drawing pictures. Its entire rendering pipeline was built around a singular goal, taking 3D shapes, figuring out what color they should be, and putting those colored pixels on a screen.
But our ocean is not just a picture anymore.
No.
It is a massive ongoing mathematical physics simulation.
Yeah.
So how did developers actually pull off fluid simulations in the old WebGL2 days? I mean, they did do it somewhat.
They did, but they had to rely on elaborate, crazy workarounds.
Like what?
Well, in WebGL2, if you wanted to do general-purpose mathematical computation on the graphics card, say, calculating our complex Fourier transforms, you had to actively trick the graphics pipeline into doing it.
How do you trick a graphics pipeline? That sounds exhausting.
It was. You would take your raw mathematical data and you would encode it into the color channels of a floating point texture.
Wait, what?
You would literally instruct the program to pretend that your physical physics variables were red, green, and blue pixel values.
That is insane.
And then you would draw a flat, full-screen square that covered the entire canvas.
You just draw a giant square.
Yeah. And you would write what is called a fragment shader.
Yeah.
Now, normally a fragment shader is a small program designed to calculate how light hits a pixel to determine its final color. But instead of calculating lighting, developers would hijack the shader, program it to execute the complex FFT math, read the quote-unquote colors from the previous texture as input data, do the math, and output the new mathematical results as new colors to a completely new texture.
Okay, so it is literally like trying to do complex calculus by painting a spreadsheet onto a canvas, taking a photo of it, and then repainting a new spreadsheet based on the colors in the photo.
That is incredibly accurate, yeah.
It is a wildly inefficient way to use hardware.
Yeah.
But WebGPU changes the game entirely, right? WebGPU lets you just open the calculator and do the math natively on the graphics card.
Exactly. WebGPU introduces a feature that WebGL never possessed natively: compute shaders.
Compute shaders.
These are written with a specific @compute tag, and they exist completely outside of the traditional graphics pipeline. They don't care about pixels or colors or drawing triangles at all.
They just crunch numbers.
They exist solely for high-performance, general-purpose parallel computing.
And to feed those compute cheaters, WebGPU introduces another massive upgrade: storage buffers.
Yes. In the WebGL era, the memory architecture was highly restrictive. Textures were mostly read-only during a draw pass, and the output frame buffers were write-only.
Right.
A program couldn't just freely read and write data wherever it wanted in the video memory. It was locked down. WebGPU's storage buffers tear down that wall completely.
How so?
They allowed the thousands of concurrent threads inside a compute shader to read from and write directly to arbitrary memory addresses in the video RAM.
And this specific feature is what makes our ocean simulation possible, isn't it? Because the fast Fourier transform algorithm doesn't just happen in one clean pass.
No, it doesn't.
It operates in multiple stages. It uses a specific algorithmic structure called a stock and butterfly, which requires the data to be processed, reorganized, and processed again, multiple times.
Under the old WebGL constraints, passing data between these various stages required intermediate texture read transitions. The GPU would literally have to stop its calculations, write the output to a texture, unbind that texture, bind a new texture, and then start the next stage. It created a massive stuttering bottleneck in the rendering pipeline.
But with WebGPU and read-write storage buffers, we implement a ping-pong buffer technique.
Exactly. Because the compute threads can read and write freely, we can simply bounce the data back and forth between two buffers residing in the memory.
Just ping-ponging it.
Right. It eliminates the need for all those intermediate texture transitions. We can execute multiple stages of the Stockham butterfly algorithm in a single compute pass. The performance gains are astronomical.
But there's a catch.
Always a catch.
Whenever we push boundaries like this, there's always a catch. Even with all this raw compute power unlocked on the GPU, there's a massive latency bottleneck lurking deep in the architecture of modern browsers.
Yeah.
The CPU-GPU memory barrier.
This is a critical hurdle for any complex simulation architecture. Let's visualize the state of our simulation right now for a second. Your graphics card, the GPU, is running these brilliant compute shaders, doing all this blazing fast math to figure out exactly where the physical waves are peaking and troughing.
Right.
But the physics engine, the part of the code that figures out where our boat is, how much it weighs, and how it reacts to gravity, is usually running on the central processor, the CPU, written in standard JavaScript or WebAssembly.
So the boat's brain is running on the CPU, but the physical shape of the ocean lives entirely on the GPU.
Yes.
Which means every single frame, the CPU needs to pause and ask the GPU, hey, what is the exact height of the water at the boat's current coordinates?
And asking that question across the memory barrier is incredibly expensive.
Why?
To read data back from the GPU to the CPU in the WebGPU ecosystem, you are forced to use an asynchronous command called map async. You have to ask the GPU to copy the requested data into a specific staging buffer that the CPU is allowed to see.
Okay.
And then crucially, you have to wait for that transfer to complete.
And according to the research, that round trip, that wait time, introduces a latency of about 2.5 milliseconds.
Right.
Now, if you are just browsing a web page, 2.5 milliseconds sounds like absolutely nothing.
It's unnoticeable.
But in the realm of real-time physics simulations and video games, we are operating on a remarkably strict frame budget. If you want your simulation to run at a smooth 60 frames per second, you only have 16.67 milliseconds to do everything.
Total.
You have 16 milliseconds to calculate the waves, calculate the boat physics, calculate the lighting, draw the foam, and push the frame to the monitor.
So taking a 2.5 millisecond penalty just to copy a small piece of data across the barrier is completely devastating.
And a massive chunk of time.
That memory readback is roughly 285 times slower than a native memory copy happening purely within the GPU's own RAM. If you block your main CPU thread waiting for that readback, your frame rate will stutter, hitch, and ultimately die.
So we have this incredible mathematical ocean, but the boat's brain can't talk to it fast enough. How do the engineers fix it?
They use one of the most brilliant architectural features of WebGPU.
Indirect dispatch.
Yes. Indirect dispatch is the moment we truly sever the cord between the CPU and the GPU during the frame execution.
Wow.
Traditionally, the CPU is the orchestrator. Even if the GPU is doing the heavy lifting, the CPU has to tell the GPU exactly how many compute threads to launch for the next stage of calculations. The CPU says, launch 100 threads to process the physics.
But with indirect dispatch, specifically utilizing the dispatch workgroup's indirect command, we completely change the chain of command.
We do. A compute shader running on the GPU processes the wave data. Then, instead of sending that data back to the CPU, that exact same compute shader writes the required thread count for the next physics step directly into a device-resident buffer located in the video RAM.
Wait, really?
Yes. Then the next compute shader is launched indirectly. It reads its own launch parameters straight from that VRAM buffer, completely bypassing the CPU.
That is wild. The GPU is literally telling itself what to do next. The CPU kicks off the frame, and then it just goes to sleep. The entire state of the ocean, the massive displacement grids, the complex physics calculations, and the dispatch sizes, it all lives natively in the video RAM.
Zero latency.
Zero latency. We have entirely eliminated the memory barrier bottleneck.
It is a masterclass in modern hardware utilization. By leveraging compute shaders to run the math natively, storage buffers to ping-pong the data without texture bottlenecks, and indirect dispatch to sever the CPU connection entirely, WebGPU provides the raw horsepower required to simulate a multi-cascade spectral ocean without melting the browser.
Okay, so we have built our ocean. The math is incredibly complex. It is running at blistering speeds natively on the graphics card, and it looks terrifyingly real.
Right.
But an empty ocean is just a fancy screensaver. We need to introduce our vessel. We need to drop a boat into this churning water. But how does a computer actually track the physical movement of a rigid object in three-dimensional space?
When we talk about rigid body dynamics in physics engineering, we rely on a framework called 6 degrees of freedom, or 6DOF. Any unconstrained object in 3D space can move in exactly 6 fundamental ways.
Let's walk through them because this applies to everything from submarines to spacecraft, right?
Yeah, everything.
First, we have the three translations. Translation is just linear movement along an axis. There is surge, which is longitudinal movement sliding forward or backward.
Yep.
There is sway, which is transverse movement sliding directly side to side. And there is heave, which is vertical displacement moving straight up or straight down.
Those dictate where the object is located in space, but we also have to track how the object is pointing.
The rotations.
Right, those are the three rotations. Roll is rotating side to side around the longitudinal axis, like an airplane tipping its wings. Pitch is tilting the nose up and down around the transverse axis. And yaw is rotating left or right around the vertical axis, exactly like steering a car.
Surge, sway, heave, roll, pitch, yaw. To track all 6 of these movements simultaneously and accurately, the simulation mathematics require a dual coordinate system.
You cannot calculate complex, rigid body physics using just a single grid. You have to maintain the absolute inertial, Earth-centered, Earth-fixed frame, often abbreviated as ECF.
Okay, ECF?
You can think of this as the global map. It tracks exactly where the boat is located in the world, and it tracks how the massive ocean waves are propagating globally across the environment.
But the hull of the boat does not care about the global map when a wave slams into its side.
Not at all.
The boat only cares about its own local orientation. I mean, a wave hitting the front of the boat feels very different than a wave hitting the side of the boat, regardless of which way north is.
Exactly, which is why the simulation must simultaneously maintain a body-fixed frame. The origin point of this local coordinate system is pinned directly to the vessel's physical center of gravity.
That makes sense.
When we calculate the linear velocity vector, how fast the boat is surging, swaying, or heaving, or when we calculate the angular rate vector, how fast it is rolling, pitching, or yawing, we must evaluate all of those forces within the local body-fixed frame.
So the computer is constantly, frantically translating the math back and forth between the global Earth grid and the local boat grid, thousands of times a second.
Yeah.
And here is where developers run into a massive, historically catastrophic mathematical trap calculating the rotation.
Oh, yeah.
Because when people first start programming 3D rotation, they almost always reach for Euler angles.
Euler angles are deeply intuitive to the human brain. You simply say, rotate the object 30 degrees on the x-axis, then rotate it 45 degrees on the y-axis, then rotate it 10 degrees on the z-axis.
Right.
It is easy to visualize, and it works perfectly fine for a lot of simple applications.
But mathematically, Euler angles harbor a fatal flaw when applied to complex, unconstrained 6DOF movement.
Yeah.
The flaw stems from the fact that Euler angles must be calculated sequentially, one after the other.
Yes, that sequence is the problem.
If we use the standard aerospace sequence, meaning the computer calculates the yaw rotation first, then the pitch, then the roll, we can encounter a terrifying mathematical singularity known as gimbal lock.
Gimbal lock occurs when a vessel pitches to an extreme angle, usually approaching exactly 90 degrees straight up or straight down.
Okay.
Because the mathematical rotations are applied in a strict sequence, as the pitch angle reaches 90 degrees, the axis used to calculate yaw and the axis used to calculate roll suddenly swing into perfect alignment with each other.
Wait, so the axes merge?
Exactly. The 3 separate rings of rotation collapse into 2 rings. You literally lose an entire dimension of rotational freedom. The math dividing the axes breaks down completely.
That sounds bad.
It's terrible.
Yeah.
If you hit gimbal lock in a simulation, your 3D object doesn't just stop. It will start spinning wildly and unpredictably, teleporting its rotation frame by frame.
Oh, wow.
And this isn't just a video game glitch either. This famously plagued the Apollo 11 moon mission.
Really?
Yes. The spacecraft's physical inertial measurement unit used sequential mechanical gimbals, and the astronauts had to actively manually pilot the craft to avoid pitching into the gimbal lock threshold, or they would have completely lost their navigation targeting.
That is intense. So to completely immunize our boat simulation against this singularity, we have to abandon Euler angles entirely. Instead, the simulation handles all rotational tracking using quaternions.
Ah, quaternions.
I remember seeing the word quaternion in computer science classes, and it is universally dreaded. It sounds like deeply complex 4D math.
Yeah.
How do we understand what a quaternion is doing without getting lost in the calculus?
The easiest way to conceptualize a quaternion is to focus on what it avoids. A quaternion represents a rotation not as a sequence of 3 separate angles turning one after another, but as a single unified rotation around one arbitrary 3D axis.
Okay.
It takes the 3 spatial dimensions and couples them with a scalar real part.
So instead of turning 3 separate dials to point the boat in a new direction, the math creates a bespoke axis, like a customized invisible pole running through the boat at the exact perfect angle, and just spins the boat around that single pole once.
That is an excellent analogy, yes. By using a 4D mathematical construct to dictate a 3D rotation, we completely bypass the sequential nature of Euler angles.
And thus, we completely bypass gimbal lock.
Exactly. Our virtual boat can pitch straight up a massive wave, roll completely upside down, and yaw violently all at the exact same time, and the underlying math remains perfectly, unconditionally stable.
That is amazing.
The simulation continuously reevaluates a direction cosine matrix every single frame based on the orientation quaternion, allowing it to translate fluidly between the Earth frame and the body frame.
Okay, so we can crack the vessel without the math shattering. Now we have to calculate the actual physical forces acting upon the hull. The physics engine governs this using a massive, intimidating formula called the mass spring damper equation of motion.
It looks like an absolute alphabet soup of calculus when written out, but it is conceptually beautiful. Think of the equation as a massive tug of war.
Okay, let's break down the teams in this tug of war. On one side, we have the inertia of the boat itself. The math calculates the rigid body mass and the inertia matrix. Essentially, how heavy is this vessel, and exactly how is that weight distributed from the bow to the stern?
But the boat is not moving through a vacuum. It is moving through water, which is incredibly dense. When a boat hull surges forward or heaves upward, it does not just move its own mass.
What else does it move?
It physically drags a massive volume of entrained water along with it.
Water literally sticks to the hull and fights the movement.
We call this added mass. In hydrodynamics, this water acts exactly like extra invisible weight bolted directly to the hull.
Wow.
And it is entirely dynamic. The added mass changes continuously depending on the exact frequency of the boat's oscillation and the shape of the hull pushing through the fluid. So the total effective mass the simulation has to move is the actual weight of the boat plus this invisible shifting added mass.
Then we have the damping forces. This is the energy the boat loses to the surrounding environment. As the boat rocks, it loses kinetic energy through the raw friction of the water scraping against the hull, and it loses energy by radiating its own small waves outward into the ocean.
Working against that damping is the restoring stiffness. This is the fundamental desire of the boat to snap back to an upright, stable resting position. It represents the hydrostatic self-righting capability engineered into the hull's shape.
And finally, pulling on the other side of the tug-of-war, we have the dynamic wave excitation force. This is the actual kinetic energy of the chaotic ocean waves physically crashing into the hull over time.
Yes.
The equation constantly balances the excitation force against the mass, the damping, and the restoring stiffness to figure out exactly where the boat should move next.
I want to focus on that restoring stiffness for a moment because this connects the abstract math directly to how a boat actually feels to a human passenger. Naval architects measure this restoring force using a concept called metacentric height, commonly abbreviated as GM.
It's fascinating. Metacentric height dictates the fundamental roll stability of the vessel.
Yes.
It is the vertical distance between the vessel's actual center of gravity and its theoretical metacenter, which is the invisible pivot point floating in the air above the deck that the boat mathematically rolls around.
The sources outline a brilliant, simplified formula for calculating the natural rolling period of a vessel based on this metric. It heavily relies on the beam, or the width, of the hull, divided by the square root of that metacentric height.
And this one formula explains nearly everything about real-world boating comfort.
It really does.
The canoe versus the raft analogy perfectly illustrates this. Think about a standard canoe. You are sitting in it, so the center of gravity is relatively high compared to the hull width. This means the canoe has a very low metacentric height.
Right.
Because the GM is low, the restoring force is weak, a canoe tips over very easily. But, crucially, until the exact moment you capsize, a canoe is incredibly comfortable to sit in on choppy water. It rolls very gently, slowly swaying back and forth with the waves.
Now contrast that with a wide, flat wooden raft. A raft has a massive beam and a very low center of gravity, giving it an enormously high metacentric height.
Okay.
The restoring stiffness is aggressive. A raft is incredibly stable. It is almost physically impossible to flip it over.
But because the metacentric height sits in the denominator of our roll period equation, a massive GM results in a very, very short natural roll period.
Exactly.
If you take that raft into the ocean, it doesn't roll gently. The massive restoring force violently snaps the raft back to parallel with every single passing wave. It creates a rapid, jerky, terrifyingly uncomfortable ride.
Ship designers are constantly locked in a battle to balance the metacentric height. If they engineer it too low, the ship will roll slowly and comfortably. But if it encounters a train of waves that perfectly matches its natural roll frequency, the rolling will amplify until the ship experiences a synchronous capsize.
It's terrifying.
But if they engineer the GM too high, the ship becomes so perfectly stable that it violently snaps back against the waves, generating such aggressive inertial accelerations that the crew becomes violently seasick, and the sheer G-forces can literally snap the ship's masts or tear heavy crane booms right off the deck.
The simulation is calculating all of this localized metacentric tension on the GPU, frame by frame.
It's incredible.
But the simulation doesn't just stop at buoyancy. We also have to consider how the boat moves forward through the water and how the forces change depending on the speed.
The hydrodynamics completely shift as a vessel accelerates. We move through very distinct physical regimes, and the map has to dynamically keep up with the transition.
Let's go through them.
When you are moving slowly, you are in the displacement regime. The boat is heavy, it is pushing a massive volume of water out of the way, and it is supported almost entirely by standard hydrostatic buoyancy.
But as you push the throttle forward, you hit the transition regime. The bow of the boat starts to pitch up, fighting to climb over its own bow wave.
All right.
The support shifts. You are no longer just floating in trodge. The hull is starting to be supported by dynamic hydrodynamic lift generated by the forward speed.
Push the throttle even further and you break through into the planing regime. The hull lifts up and literally begins to glide over the surface of the water, skimming along supported entirely by dynamic lift, dramatically reducing drag.
That's when you're really flying.
And at the absolute extreme end, we have the foiling regime, where submerged hydrofoil wings lift the entire mass of the hull completely out of the water, essentially turning the boat into a low-altitude aircraft flying through a liquid medium.
And simulating that high-speed planing or foiling on a GPU is notoriously difficult because the physics become highly nonlinear. The hull isn't just resting in the water. It is actively skipping over chaotic wave crests, slamming violently down into troughs, and throwing up massive walls of spray.
The mathematical stability becomes incredibly sensitive at that point.
If the physics engine isn't perfectly tuned, a fast planing hull making an aggressive turn in heavy waves will experience a catastrophic spinout.
Oh, yeah.
The lateral resistance on the hull breaks, causing a massive instantaneous spike in the yaw rate and drift angle. The boat violently slides sideways, bleeding off all its forward speed and generating massive centrifugal G-forces that would throw a crew overboard in reality. The simulation has to account for all of these edge cases.
So we have this beautifully complex mathematical brain for our boat, calculating 6 degrees of freedom using quaternion rotation, tracking metacentric height, and fighting through hydrodynamic regimes.
Right.
But this brings us to the multi-million-dollar question, the core of the entire simulation. We have the boat and we have the water. But how does the boat actually know where the water is?
How do they interact?
Exactly. How do the two separate mathematical entities physically interact with each other in the code?
This is where we transition into the specific techniques of GPU-driven voxel buoyancy.
Yeah.
We have to design the interaction layer.
For the Sigma scholars tuning in, to understand the interaction layer, we have to strip the calculus away for a second and start with the absolute fundamental basics of floating. We have to talk about Archimedes' principle.
Formulated over 2,000 years ago in ancient Greece. And it is still the undeniable core of our cutting-edge WebGPU physics engine.
It's amazing.
Archimedes' principle states that the upward buoyant force acting on a submerged object is directly equal to the weight of the fluid that the object displaces.
The formula is relatively simple. The buoyant force equals the density of the fluid, multiplied by the displaced volume, multiplied by gravity.
Right.
Now, we already know the density of seawater is constant. We know the force of gravity is constant. So the entire agonizing challenge of writing a buoyancy simulation boils down to calculating one single, constantly changing variable.
Finding the exact displaced volume.
Precisely. We need to find the exact mathematical volume of a complex, curved, 3D boat hull that is currently intercepting with a chaotic, multi-layered, rapidly changing FFT wave surface. And we need to calculate that exact intersecting volume 60 times every single second.
The research highlights two main computational approaches to solving this volume problem. The first approach is highly analytical. It is called wetted surface triangle clipping.
In the triangle clipping method, the processor looks at every single geometric triangle that makes up the 3D mesh of the boat's hull. It compares the position of each triangle against the dynamic height of the wave surface at that specific coordinate. It then mathematically cuts the polygons exactly at the waterline. It discards the dry upper parts of the hull, and it generates entirely new, dynamically created smaller triangles that represent only the submerged portion of the hull.
It sounds incredibly precise.
Yeah.
You are literally slicing the geometry at the water level, frame by frame.
It is remarkably precise.
Huh?
By summing up the geometric volume of all those newly clipped underwater triangles, you get a highly accurate measurement of the displaced volume.
Right.
You also get an exact calculation of the wetted surface area, which is vital for calculating accurate fluid friction drag. However, doing complex polygon clipping dynamically on a GPU is notoriously difficult and computationally expensive.
Why does the GPU struggle with it?
Because it requires intense branching logic. GPUs are designed to do the exact same mathematical operation thousands of times simultaneously. When you ask a GPU to look at a triangle and say, if it is above water, do this, but if it is halfway underwater, slice it here and create 3 new vertices, but if it is fully underwater, do something else, that branching if-then logic shatters the parallel processing efficiency. It chokes the hardware.
Which is exactly why the state-of-the-art approach in modern WebGPU simulations completely abandons triangles for the buoyancy calculation. Instead, we use GPU-driven voxelization.
Voxelization is computationally elegant because it removes the complex geometric intersection math entirely. A voxel is just a 3D pixel. It is a simple uniform volume element, essentially a tiny mathematical cube.
Think of it like taking a sleek, beautiful 3D model of a boat, like the intricate Sabot Casablanca-class escort carrier model mentioned in Phil Crowther's aviation repository, and completely filling its interior volume with a dense 3D grid of tiny blocks. We essentially turn the highly detailed boat into a Minecraft creation for the physics engine.
That is exactly what happens under the hood. Before the simulation even starts, or processed dynamically on the GPU, we subdivide the total mass and volume of the ship equally among thousands of these individual voxels.
And the brilliance of this approach is how simple the buoyancy calculation becomes. Instead of trying to mathematically slice intersecting polygons, our compute shader just looks at every single voxel independently and asks one incredibly simple question.
Is the center coordinate of this specific block lower than the localized wave height at this exact same spot?
Simply put, is this block wet?
If the answer is yes, the block is submerged. The compute shader instantly applies a localized upward Archimedes force vector to that specific block.
It's that simple.
By doing this across thousands of voxels simultaneously and a massive parallel reduction on the GPU, we naturally generate the total buoyant force. But more importantly, because the upward force is distributed specifically among the wet blocks, we naturally calculate the precise center of buoyancy, which dynamically dictates the pitch and roll torque acting on the hull.
It is a brilliantly simple workaround to a complex geometric problem. But when developers actually implement this pure voxel logic for the first time, they almost always run into a hilarious game-breaking physics bug.
Oh, the rocket launch problem.
Yes. It is colloquially known as the rocket launch problem.
Ah, yes. The rocket launch bug is a perfect example of numerical instability in physics simulations.
Imagine a scenario where our virtual boat falls from the sky, or gets plunged deep underwater by a massive rogue wave. For a brief moment, every single voxel in the hull is deeply submerged.
Right.
According to our pure Archimedes logic, the simulation applies maximum upward force to every single block simultaneously. The boat generates so much upward velocity that when it finally breaches the surface of the water, it doesn't just organically bob.
No, it flies.
The math slingshots it completely out of the ocean, launching it into the virtual sky like a Trident missile.
The simulation breaks because pure Archimedes buoyancy only calculates the static upward force. It completely fails to account for the viscosity and dynamic drag of the water actively resisting the boat's upward ascent. The water should act like a brake, but pure Archimedes logic treats the water like a frictionless vacuum.
So how do we fix the mass to stop the boats from entering orbit?
The compute shader has to apply a localized velocity damping force. We don't just calculate the position of each voxel, we calculate the world space velocity of each voxel.
Okay.
If a submerged voxel is moving upward toward the surface at a high velocity, the compute shader applies a dampening force in the exact opposite direction, simulating the drag of the water pushing back against the hull.
The sources also mentioned adding a depth scale clamp near the surface to smooth things out.
Yes, the depth clamp is crucial for preventing high-frequency numerical jitter. If a voxel is hovering exactly at the waterline, dipping in and out of the water frame by frame, it will wildly toggle between having maximum buoyant force and zero buoyant force.
Which would look terrible.
It causes the entire boat mesh to visibly vibrate and jitter unnaturally. By smoothly scaling down the buoyant force as the voxel approaches the exact surface, creating a gradient of force rather than a hard on-off switch, the physics settle smoothly.
The result is a profoundly stable, highly localized buoyancy system that completely respects the chaotic, multi-layered wave shapes, allowing the heavy mass spring damper equations to settle naturally without breaking the simulation.
So, if we take stock of where we are, the underlying mathematics are sound. The boat's brain is processing 6 degrees of freedom using quaternion rotation to avoid gimbal lock. The voxel grid is calculating localized Archimedes buoyancy while applying velocity damping to prevent rocket launches.
Right.
The hull is actively bobbing and rolling perfectly on top of the complex IFFT-generated ocean surface. We have achieved a highly robust physical simulation.
We have the physics, but to truly impress the Sigma scholars, this digital twin needs to look viscerally real. A mathematically perfect wireframe grid bobbing on another wireframe grid doesn't feel like the ocean.
It doesn't.
It needs to look like a living, breathing, terrifying environment. We need optical physics, and we need chaotic water splashes.
Which brings us to the final layer of the simulation. Because WebGPU affords us so much raw parallel compute power, we no longer have to fake the visual effects with clever animations.
Right.
We can derive the visual phenomena directly from the underlying physical state of the water. Let's start with the surface itself, white caps, and wave breaking. How does the simulation actually know when a wave should foam?
In older games, a developer would just say, if the wave gets taller than 3 meters, paint a white texture on top of it. But that looks fake because real waves don't break just because they are tall. They break because they get too steep.
Exactly. To simulate this accurately, we use a mathematical diagnostic tool called the Jacobian determinant.
The Jacobian determinant.
Earlier, we discussed how our ocean waves have a horizontal displacement. The mass of the water actively bunches up and pinches at the crests. The Jacobian determinant mathematically tracks the spatial compression of this 2D surface grid.
It is essentially a real-time measurement of how aggressively the wave is folding in on itself.
Precisely. The compute shader constantly calculates the Jacobian value across the entire ocean surface. If the Jacobian value drops below 1.0, it mathematically indicates that the wave surface has compressed so violently in the horizontal direction that the 3D geometry is physically about to overlap itself.
Oh, wow.
In physical fluid dynamics, this is the exact threshold where a wave becomes physically unstable. It is the moment it breaks and crashes forward.
So the compute shader just acts as a watchdog. The millisecond that Jacobian value dips below 1.0 on any vertex, boom, it triggers a physical wave-breaking event.
It instantly spawns multi-layered, mathematically generated persistent foam in a data texture overlaying that exact spot. But the visual brilliance is that the foam doesn't just sit there statically on the water.
What does it do?
It backtraces through the localized velocity field of the underlying waves. The foam gets carried physically by the virtual current, it diffuses outward over time, and it slowly decays, leaving realistic, lingering wake trails that are generated entirely by the underlying math of the wave itself, not by an artist's animation.
That perfectly handles the chaotic surface of the water. But let's dive underneath. One of the most beautiful and visually complex phenomena in a swimming pool or a shallow ocean bay is the web of dancing light patterns on the seabed, caustics.
Rendering real-time caustics is notoriously computationally punishing because light does not travel in straight, predictable lines when it passes through water.
Right.
The light rays bend or refract violently as they strike the undulating, constantly shifting surface of the waves. Some areas of the seabed receive tightly focused, intensely bright light, while adjacent areas are cast into deep, refracted shadows.
To perfectly simulate this, you would have to trace the path of millions of individual light photons from the sun, through the wave geometry down to the sand. That is called path tracing, and it is way too slow for real-time 60 frames per second applications.
Yeah.
So how do they fake it so convincingly?
The sources detail a specific technique called the differential area method.
Okay, the differential area method.
The differential area method is a brilliant shortcut. Instead of tracking millions of individual photons, we project a grid of refracted light rays through the dynamic wave surface down onto the seabed.
Right.
Then, instead of counting photons, we measure how the geometric area of the light projection changes as it hits the floor.
We measure the stretching and compressing of the light itself. To do this, we utilize WebGPU's built-in derivative functions, specifically dpdx and dpd.
Those functions are fundamental to modern shading languages. They calculate exactly how fast a specific mathematical value is changing between adjacent pixels on the screen in real time.
By measuring the derivatives of the projected light grid, we can dynamically measure the light's compression. If a wide, uniform beam of sunlight hits a sharp wave crest and gets violently refracted, focusing into a tiny concentrated spot on the seabed, the derivative functions instantly tell us that the geometric area of the light just shrank drastically.
Exactly.
Because the area shrank, the optical intensity of the light must spike.
We map that calculated intensity spike directly to our underwater lighting shader, and suddenly, without path tracing a single photon, we have breathtaking, mathematically accurate caustics dancing rapidly on the sand, reacting perfectly to the chaotic wave state above.
Okay, so we have the churning ocean, we have the mathematically generated foam, we have the dancing refracted light, but there is one massive chaotic element missing.
The splashes.
What about the specific violent splashes when the heavy boat's bow aggressively slams into a wave trough? How do we render the physical water spraying wildly into the air?
For that highly chaotic, fine-scale fluid interaction, a continuous mesh is useless. We have to transition into fluid particle systems.
Okay.
The sources highlight a massive fundamental evolution in how we simulate physical fluid particles on a GPU. Historically, physics engines relied heavily on a method called SPH, or smooth particle hydrodynamics.
SPH has been the industry standard for a long time. It essentially treats a body of water as thousands of individual tiny physical spheres continuously bouncing off of each other.
The concept makes sense visually, but the computational problem with SPH lies in the neighborhood search bottleneck.
What's that?
To accurately calculate fluid pressure and viscosity, every single particle in the simulation needs to constantly check its exact physical distance to every other particle surrounding it.
So if you only have 10 particles, that is 100 distance checks.
Yeah.
But if you have 100,000 particles to make a realistic splash, you are suddenly asking the computer to run 10 billion distance checks every single frame.
Exactly. It is a massive quadratic search problem, mathematically denoted as ON squared. As you scale up the particle count, it absolutely chokes the GPU bandwidth.
But the WebGPU Ocean and Waterball demonstration projects, highlighted in our research sources, completely abandon SPH.
They do.
They use a much newer, significantly more advanced method called MLS-MPM, the Moving Least Squares Material Point Method.
It is a massive mouthful of an acronym, but how does it actually solve the 10 billion check bottleneck?
It solves it by introducing a middleman. MLS-MPM is a hybrid computational approach. Instead of the particles constantly frantically searching for each other, the MLS-MPM method transfers the vital particle data, like their individual mass and velocity vectors, onto a fixed invisible background grid.
Right.
This initial step is called the particle-to-grid, or P2G stage.
So the particles just dump all their velocity information into the grid cells they happen to be passing through, and then the grid itself calculates the complex physical fluid forces and internal pressures.
Exactly. The grid handles the complex physics, completely eliminating the need for any quadratic neighborhood searching. Once the grid finishes calculating the updated pressures and forces, it simply transfers the updated velocity data back onto the individual particles in the G2P, or grid-to-particle stage.
By using the grid as a computational middleman, MLS-MPM completely circumvents the n-squared bottleneck. The WebGPU implementation data shows that this specific architectural shift allows a standard integrated laptop GPU to easily simulate over 100,000 fully interacting physical fluid particles in real time.
It allows for massive, violent, heavy splashes as the hull slams through the waves, 100,000 particles cascading over the bow. But here's the final visual problem.
Making it look good.
Rendering 100,000 tiny, distinct spheres on a screen looks absolutely terrible. It looks like someone dumped a massive ball pit over the boat. It doesn't look like cohesive liquid water. If we have 100,000 particles, how do we make them visually look like a solid fluid splash?
This is where we use one of the most clever rendering techniques in modern graphics, screen space fluid rendering, or SSFR.
I absolutely love this trick because it is pure optical illusion. We have 100,000 mathematical points flying through the virtual air. We could try to run a complex geometric algorithm like marching cubes to mathematically wrap a cohesive 3D geometric skin around the particle cloud.
But that's too slow.
Generating new 3D geometry every frame is way too slow.
Yeah.
So instead, we render the fluid as a 2D optical illusion.
We completely ignore 3D geometry. We take the 100,000 particles and we render them simply as depth splats onto a flat 2D depth map on the screen.
Okay.
If you were to look at this raw depth map, it would just look like a lumpy grayscale height map representing the distance of the particles from the camera.
It looks like a bumpy static image. Then, we take that 2D image and we aggressively run a bilateral filter over it. A standard blur filter would just turn the splash into a hazy, indistinguishable fog.
Yeah.
But a bilateral filter is mathematically smart. It heavily blurs the lumps together so the core volume of the water looks thick and smooth, but it actively preserves the sharp, high-contrast edges of the splash silhouette so the water doesn't lose its shape.
And the final stroke of genius is how we light it. We do not have a 3D mesh, so we do not have actual 3D geometric normals to bounce light off of, but we can mathematically reconstruct the 3D surface normals directly from the changing gradients of that smoothed 2D depth map.
That's brilliant.
The lighting shader takes those faked, reconstructed 2D normals and applies complex specular highlights, light refraction, and Fresnel reflections based on the exact camera angle.
You completely skip making an actual 3D mesh for the splashes. It is a total optical illusion that saves massive amounts of compute power, but to the player's eye, with the lighting applied, it looks exactly like a thick, heavy, contiguous volume of splashing water crashing over the deck.
It is the absolute perfect marriage of advanced, grid-based numerical simulation and brilliantly clever rendering optimization, all heavily powered and accelerated by WebGPU's unconstrained compute shader architecture.
We have journeyed so incredibly far today. For the Sigma scholars still tracking with us, let's take a step back and appreciate the massive architectural stack we just built from the ground up.
It's quite a stack.
We started by throwing away fake procedural sine waves, opting instead to generate physically accurate, chaotic ocean energy frequencies using statistical models like the John Swap spectrum.
Right.
We took that frequency data and passed it through the inverse fast Fourier transform, intelligently halving our computational workload by exploiting the Hermitian symmetrical property of real numbers.
We unleashed the raw, parallel processing power of the WebGPU API, utilizing unconstrained compute shaders and read-write storage buffers to run the heavy math natively on the graphics card.
Yes.
And we utilized the brilliance of indirect dispatch to sever the CPU bottleneck entirely, letting the GPU dictate its own physics threads, achieving virtually zero latency.
We then modeled the brain of a rigid body vessel in 6 degrees of freedom, purposefully abandoning Euler angles for 4D quaternions to defeat the catastrophic gimbal lock singularity.
Exactly.
We applied a complex mass spring damper hydrodynamic equation to balance the hull, actively calculating added mass drag and metacentric roll stability.
We dropped that mathematically complex boat hull into the water by completely voxelizing it, treating it like a dense grid of blocks, and evaluating Archimedes' upward buoyant principle block by block against the dynamic wave surface, making sure to apply localized velocity damping to prevent our boat from launching itself into orbit.
And we finally wrapped the entire simulation in a layer of stunning physics-driven optical phenomena. We actively track the spatial surface compression with the Jacobian determinant to mathematically trigger persistent wave breaking in foam.
It looks so good.
We rendered highly accurate, real-time caustics on the seabed by analyzing the screen space derivatives of refracted light grids. And we slammed the hull into the water, generating over 100,000 MLS MPM fluid particles, completely bypassing the SPH neighborhood bottleneck and rendering them seamlessly into a cohesive liquid volume using the optical illusion of screen space fluid rendering.
It is an absolute symphony of applied mathematics, advanced physics, and cutting-edge computer science, all running locally, flawlessly, inside a standard browser tab.
It really is.
Yeah.
But before we sign off and let you all recover from the math, I want to leave you with one final, deeply provocative thought to mull over.
Oh, this is a good one.
We have thoroughly established that we can now simulate hyper-realistic multi-cascade spectral oceans and highly complex 6DOF rigid body interactions natively in a web browser using WebGPU. This level of computational power is no longer locked away.
No, it is democratized.
It is sitting locally on the standard device currently sitting on your desk or in your pocket. So what happens when we stop treating this just as a rendering exercise and we hook these incredibly efficient local simulations up to live, real-world data feeds? Think about real-time global weather APIs monitoring the oceans right now.
The implications are staggering. You could open a simple browser tab on your phone, pull down live environmental data, and virtually sail a fully physically modeled 60-F vessel through the exact, mathematically precise wave conditions currently happening in the middle of a Category 5 hurricane in the Atlantic Ocean.
Rendered completely locally, in real time, driven entirely by live satellite data feeding the John Quab spectrum variables.
Mm.
What does this massive leap in accessibility mean for the future of digital twin technology? We're no longer just making visually impressive video games. We're making highly accessible, instantly deployable scientific simulations.
If any student, any engineer, or any naval architect can suddenly access a high-fidelity, mathematically robust hydrodynamic testing environment just by clicking a web link without downloading a massive engine or renting supercomputer time, how does that accelerate the pace of marine engineering?
Right.
How does it change the way we train autonomous drone vessels to navigate rough seas? How fundamentally does it change our ability to understand, predict, and interact with the incredibly chaotic energy of the open sea?
We've evolved from staring at a fake, flat geometric plane with a painted texture on it to holding a living, breathing, mathematically flawless digital twin of the ocean right in your browser. It is a brilliant time to be studying computer science. Think about it. Until next time.